Good morning, students. So today I am going to give you my third lecture, and that is on the De-Broglie wavelength or matter waves. So usually I am saying about waves and matter. Okay. So we know electromagnetic wave, and we have already studied the photoelectric effect and Compton effect. So in the photoelectric effect, I saw that photon which was coming was able to strike an electron and releasing it. And in Compton effect, the photon which was coming was making collision with the electrons. So actually, this shows that the electrons or even the photons, they are somewhere behaving like waves. Okay. Now, matters in general, if I see the dual nature of light or waves and matter is associated with all the body. It is not like any body is having the two characteristics, that is wave characteristics and mass, means mass characteristics, but only depending on their size and depending upon their our observation, we sometimes observe both the nature for certain cases, and sometimes we do not observe both the nature of the two cases. It is upon observation, but this phenomena and this property is there. Okay, so we will see in this lecture what happened, why we do not see when my car is moving with a velocity of 80 km per hour, but I can see it with electrons which are moving at a relativistic velocity of the light, means nature of. So De-Broglie actually hypothesized this concept in 1924, and the concept was every moving particle has a wave packet associated with it. We said initially the light has a wave packet, but it is now saying every moving particle will have a wave packets. Okay, so we know that lambda is given by h upon mass into velocity, where h is the Planck's constant, and again mass into velocity is called momentum. Okay, so it will be coming h by momentum p. Now, according to the Planck's hypothesis, which you have studied in the beginning of the quantum phenomena, E is equal to h nu, energy is associated with the wave frequency, and that will be given by hc upon lambda. So this equation will give me lambda is equal to hc upon E. Now we also know very famous Einstein equation of energy conversion to the mass, and from that equation we know, according to Einstein mass energy equation, E is equal to mc square. E is equal to mc square. So if I am using this value and putting it in the equation 2, I will get lambda is equal to hc upon mc square, and when the c and c will cancel, then it will become h upon mc, and hence h upon p. So lambda, where is the momentum of the photon. So this was the case of the photon. However, this case will be also true for any mass particles, okay, of the matter, and hence lambda can be written as h is equal to m into v, replacement of velocity of light with any velocity, okay, for any body. Now h is equal to h by p. So what we actually hypothesis is that the matter will behave like a wave. Any matter will behave like a wave. There is no excuse. However, observation may be different. Let's see now this equation in terms of De-Broglie wavelength in terms of kinetic energy. Means if the particle is moving with some kinetic. Now we know kinetic energy is given by half mv square. Now multiplying both up and down side by m, it will become half m square v square upon m, and that will be, since mv is equal to momentum, that will be given by p square, and then p will be equal to, from this equation, p will be equal to root over 2mk, and then from this equation we will get that lambda is become equal to root over h upon root over 2mk. For a particle, if this was the particle accelerated by physical, means like my car, motors, okay, but sometimes, but the particles can also be accelerated by the electric field, as is the case in the accelerators. So what will be happening there? Okay, kinetic energy will be equal to charge into the potential applied, charge of that particle which is being accelerated. So in this case, lambda will be equal to h upon root over 2m/v. For a particle, now the particle can sometimes accelerated by thermally heating it. So in that case, the kinetic energy of a thermally heated system or a particle will be given by k is equal to 3 by 2 upon into kT, where k is the Boltzmann constant given by k is equal to 1.38 into 10 power minus 28 joule per Kelvin, and it is also called Boltzmann constant. Putting this value again in the lambda becomes h upon root over 3mkt. You see that, and so we are seeing that if the particle get accelerated to some velocity, it will be having the wavelength associated with it. Okay, so let's see why I am not able to observe this in the case of my car driving. So if I am driving my car with a velocity of 880 km per hour, which is the general high velocity considered to high velocity, and having a mass of 1000 kg. So in this case, if I calculate the value of lambda, then lambda, if I from the equation h upon mv, then the lambda value will be coming to be 2.98 into 10 power minus 38 meter. So 10 power minus 38 meter, it is coming in the range of 10 power minus 38 meter. This is a very small wavelength, and usually till date not measurable using some experimental techniques. So in general, all the matter thus is having an associated wave, but if the matter has a really very high velocity, if let's consider this velocity of the electron and the velocity, relativistic velocity approaching to c, then in case of electrons, if it is even moving with the 1/10th time of the velocity, it will be having a sufficiently measurable value. So this happens in the most of the experiments where we measure the wavelength of the electrons and even photons, and electrons and even protons, and sometimes even heavy materials. So very interesting that De-Broglie concept of dual nature, on not only giving the dual nature but also associating a wavelength with the particle. Okay, this is today's enough, and I will be discussing next in next lectures again. Thank you very much for watching it.